Okay. So we've got a look at three-part B. I might do all of it because it's a bit repetitive calculations involved, but we'll find some of the solutions. So here you've got a polynomial f of x, which is specified as x squared minus 90x plus 99. This is congruent to 0 modulo 125. The key thing about 125, of course, is that that is 5 cubed. That's its prime factorization. And the question says use the result concerning solution lifting to find all the solutions of this polynomial. The result concerning solution lifting is Theorem 7.2, which is included on the handout. It's not something you're expected to remember off by heart. And this theorem works by, it tells you that if you've got a solution to this, one, which is some polynomial congruent to 0 modulo some power of p, this theorem, this result tells you how to generate associated solutions to the same polynomial congruent to 0, but modulo, here it's written as p to the a. So with what you did have a solution already, modulo p to the a minus 1, and this theorem tells you if and how that solution lifts to the next possible power in the ladder of powers. Okay. So this is going to lead us through this kind of inductive or repetitive process where we start with solving the polynomial modulo just p on its own, modulo 5, and then whatever solutions we can find there, this will tell us how to build them up, how to bring them up to the polynomial congruent to 0 modulo 125. It's a decision procedure. There's various things to check. You have to check how the derivative of the polynomial evaluates modulo p. And if the derivative of the polynomial evaluates to 0 modulo p at one of the solutions you already have, then there's a further check to make, which is based on the value of the polynomial modulo p to the new power, and so on. And the type of lifting that goes on, here the solution lifts uniquely. So your one solution to the polynomial modulo p to the a minus 1 produces one solution to the next power. If you find yourself in this part describes how the solution, what's the best word, how it, tempted to say bifurcates, but that's not quite right. So produces many solutions. Well, in fact, it produces p different solutions. So sometimes the solution you have lifts uniquely. Sometimes it generates multiple solutions, namely p different solutions to the polynomial modulo the next power. And this last part, if you're into this last part here, then it doesn't lift. So the solution you had, modulo p to the a minus 1, does not generate an associated solution modulo the next power. And if you do this process with all of the solutions that you have at the level p to the a minus 1, then this will generate for you all the solutions that there are modulo the next level, p to the a. So the specification of this is all in the handout, and you just have to be, just familiar with using it and following the requirements. Okay. So let's have a look at one of these examples. So that's on page 52 of the notes. So it'll be helpful if you have that open beside you. Doing this. So we begin by solving f of x congruent to 0 modulo 5. The thing is quadratic, so we know by Legendre's theorem, the Bayes theorem. Keep on forgetting to do this associated to Lagrange. There we go. Look, we know by Lagrange's theorem, because f is quadratic, this has at most two solutions. So that's good to know in upper bounds. We know if we do identify two solutions, we'll know that there aren't any more. Lagrange's theorem only applies in the case where the modulus is a prime. So that consideration only applies at this bottom level. Modulo 125, there could be quite a few solutions. But of course, the polynomial, when you talk about it modulo 5, it simplifies a lot, because I can apply the congruence modulo 5. And when you've got this kind of combination under addition and multiplication, this arithmetic combination, you can just reduce everything modulo 5. Okay? So the 90 is 0 modulo 5. So there is no x term, because it's just multiplied by x. And the 99 is minus 1 modulo 5, or 4 modulo 5, if you like. No, let's just write it as 4. 0, 5. So this is equivalent to saying x squared is congruent to minus 4 modulo 5. But that's equivalent to saying x squared is congruent to 1 modulo. Minus 4 is congruent to 1. The distance between minus 4 and 1 is 5. And the two solutions to 2 square roots of 1 modulo 5, well, there are two, namely x congruent to 1 or minus 1 modulo 5, or you might prefer to say that as 1 and 4 modulo. Let's stick with the 1 and 4, since they're our stat. We normally take the least positive residue, standard residue for a certain congruence class. But it is crucial to recognize when you are looking at the congruence class of minus 1, because that normally has certain properties. So is that part okay? It is. We've got two solutions at the bottom level. So each of these we need to lift up to the 125 level using the result. So firstly, let r equal 1, and we seek to lift this to solution or solutions modulo 5 squared, 25. Okay. Using, well, here we'll be using theorem 7.2. Because in an exam situation, you don't have to remember that number 7.2. Just refer to it as the lifting result from the handout. So the first thing we got to check is we got to evaluate the derivative of the polynomial at this solution that we have, and check whether it's 0 or non-zero modulo 5. So the derivative of the polynomial is 2x minus 90. When you evaluate that at 1, evaluate that at the current solution, it's 2 minus 90, which is equal to minus 88. Which, whatever it is, well, let's just reduce that modulo 5, so that's equivalent to 2 modulo 5. So that is certainly non-zero modulo 5. So this R solution, so R equals 1 will lift to a unique solution. The result, this is called S, unique solution S, to f of x congruent to 0 mod 25. And this is given by, so the formula for S is R plus r plus 5t. So when you're using the result, as you can see in page 52, so be very careful you get all the exponents and the moduli correct at each stage. Now what's this t for t? It's the unique solution to the linear congruence this linear congruence t times f prime of r. Well, f prime of r we already worked out was minus 88. Plus f of r, okay, we haven't identified that yet. So f of r f of 1, which is 1 minus 90 plus 99. What's that? 100 minus 90 is 10. So plus 10 over 5. So common to 0 modulo p. So we just have to solve this now. Minus 88, we already decided that was 2. So congruent to 2. 10 over 5 is of course 2. This is congruent to 0 modulo p. So that's going to be true if t is congruent to minus 1. Sorry, this p is 5, sorry. T is congruent to minus 1, i.e. 4 modulo 5. Clearly t has to be minus 1 modulo 5, so that you have minus 2 plus 2 congruent to 0. Minus 6. So that's the value of t, which goes in here. So the new solution S is equal to 1 plus 5.4, which is 21. So that's our solution to the polynomial modulo 25. So you just need to lift it again to get up to a solution modulo 125. I'll just do this stage, which will be half of it, and then you would have to go back and start again with the original solution, r equals minus 1, and lift that up through the powers of 5 as well. So now apply the result again with r equals 21. This is a solution to f of x congruent to 0 modulo 25. To lift to a solution or solutions modulo 125. We're double checking things along the way as you go, because it would be bad to make a mistake early on and then to carry that through. So, do double check things as you go, and I suppose a calculator might be a little bit useful here to give a bit more confidence or speed you up a bit. So we go through the same process. We again have to check the derivative of the polynomial. Because that's the first check you do is this solid, it's a bullet point. So checking the value of the polynomial at the current solution tells you whether you go into this top paragraph or this bottom paragraph. If you go into the bottom paragraph, there's this further check where you're checking the value of the polynomial modulo the new power of p. So we check f prime evaluated at 21. So we've got f prime is 2x minus 90. So this is going to be 2 times 21 minus 90. So this is what's that? 42 minus 90 is whatever it is, minus 48. Which, whatever that is certainly non-zero modulo 5. So we're into that top paragraph. So again, the solution is lifted uniquely. So we get the unique solution S, use solution given by S is formula, so t times f prime of r. So f prime of r here is minus 48. So minus 48 times t. R formula r, which is 21, plus e to the a minus 1 times t, plus 25 times t. 25 times t, or t. T is the solution to, so this is the one with f prime r, which is minus 48 times t, plus f of r, so I need f of r here. So the polynomial evaluated at 21, which is 21 squared minus 90 times 21 plus 99 squared 441 and 95 minus 1890 plus 99. 1890 441 minus that is 9, 4, 18 minus 4 is 14. So that's minus 1449 plus 99, which is at 100, will be minus 13. 40. Minus 1350, is that it? You got a calculator? Yeah, minus 1350. Subtracting negative numbers, isn't it? Minus 1350, number to 0, modulo 5. Oh no, sorry, it's minus 1350 divided by 25. I'm solving this modulo 5. And minus 48, let's leave that alone for a moment. So do that division, what does that divide? 5 times 104 times, so that's 13 times 4. 13 times 4 is 40, 12, 52, and then next to 2, 54, so minus 54. Okay, t is minus 48 is 2 again. And minus 54 is 1. 0 modulo 5. So 2t is congruent to 1 modulo 5. So t is congruent to 3. So t is 3. So you just feed that back in up here. So the top level solution S is 21 plus 25 by 3, so 21 plus 75, 96. So this is the solution to f of x congruent to 0 modulo 125. So that's kind of half the work. The other half the work is to go back and lift the solution minus 1. Not my favorite type of exam question, to be honest. It's a little bit repetitive. Once you've lifted at one stage, it's really just going through exactly the same steps to lift it to the next stage. But any questions about it? Or and I'm only about 60% confident that it's correct. Just so much calculation. But try. What is f of x? Let's just check. F of, so it's supposed to be 96. Could someone with a calculator do 96 squared minus 90 times 96 plus 99? That.
675. 675.
675. And does 125 divide 675? Better.
Was it? No, not whole. 5.4. Where do we go wrong?
Wait, Killian, is it where minus 54 would be converted to -1, so it would be -1 plus 1?
Sorry, yeah, excellent. Yeah, so it's just here. Yeah. Minus 54 is congruent to 1. No, it's congruent to -1. No,
54 is called
54 is -1, but there's an extra minus sign, so that should be a plus 1.
Well done. That's not too far back, so that's congruent to 1, so that's a -1, which is 4, so t is congruent to 2. So that's 2. So 5071. Yeah, so surely 71. Let's just double check that.
Got that evaluation for us.
So it's definitely advisable to check. And again, yeah,
All these pluses and minus signs are a bit hazy.
Minus 1,250.
-1250, which is of course
A multiple of 125. Yeah, cool.
okay, great. Okay, let's move on to question 4. A bit more interesting stuff in question 4. So for part A, you've got a linear congruence to solve. Use the relevant results of the theory of congruences to describe all of its solutions, modulo 21. In part B, there's an instance of applying the Chinese remainder theorem to lift 3 different congruence classes. Find a unique congruence class modulo a higher power, representing all those. Then there's a little descriptive question, which is to apply basically to derive the quadratic formula, again for solving a quadratic congruence, not an equation of congruence. You're basically going through the same derivation as obtaining the quadratic formula for quadratic equation, but this time for congruences, so just a couple of the concepts need to be modified. And that also links us into the question of quadratic residues. And then part D is basically evaluating a Legendre symbol to work out if 461 is a quadratic residue modulo 773. And to talk about, show how the various properties of the Legendre symbol combine to enable you to solve questions like 4 part A. Okay, let's try and get to these. So for part A, again, there's a result which is completely describes the linear congruences. It's in chapter 6. It again is on the handout, but you do need to know how to work with it, how to navigate with it. So it's this one, Theorem 6.3. So we'll be applying that. So the basic idea is this kind of thing mightn't have any solutions. It's not guaranteed to have solutions. What we have to check is we have to work out the GCD of the coefficient of x and the modulus. This comes out to be 6 and 21, so that's going to be 3, isn't it? GCD of these. And then you check whether this GCD you found, whether that divides the constant term 9, which it does. 3 does divide 9. So that means there will exist solutions. Will exist, and there will be 3 of them. 3 of them, because this 3 is the same as that 3, GCD figure. 3 of them modulo 21. To find them, you need to reduce the modulus to reduce the congruence. So we reduce the original congruence by dividing across by 3. So 6x congruent to 9 modulo 21. This is going to be satisfied by an integer x, and only if the x also satisfies 2x congruent to 3 modulo 7.
Okay, so you divide all three parts of the congruence by this GCD. And because you've divided by the greatest common divisor, this 2 is now co-prime to the modulus, okay? Because whatever greatest common divisor the coefficient of x in the modulus had, you've now removed it. So this 2 is now co-prime.
So it has an inverse modulo 7. So the solution x is just going to be the inverse of 2 multiplied by 3 modulo 7.
So what is the inverse of 2 modulo 7? Yeah, 4. 2 times 4 is 8, which is clearly congruent to 1. So the inverse of 2 is 4.
So this solution is just x congruent to 4 by 3 is 12, but that, of course, we represent that as 5 modulo 7. Okay.
So that's our solution to the problem, is that the integers x which solve that come from, or is everything from the congruence class of 5 modulo 7.
But the original problem was posed modulo 21, so you've got to
Lift this up to modulo 21, and the congruence class of 5 modulo 7 basically comes from 3 different congruence classes. There are 3 different congruence classes modulo 21. One of them is represented by 5 mod 21. Just keep on adding 7s. The other one will be 12 mod 21, and the other one then will be 19 modulo 21. These 3 congruence classes modulo 21 are the lift of 5 modulo 7. If you add another 7, you get 26. That's back inside this congruence class. So there are only 3.
So the 3 solutions to the original congruence are represented by x congruent to 5, keep adding 7s, 5, 12, and 19, modulo 26.
That all comes from that result about linear congruences on the handout. Of course, when I'm writing this 2 inverse, context here is modulo 7, so the 2 inverse is equal to the inverse of 2 modulo 7.
Any questions about that? Or
What? Sorry.
what did I say, 26?
26 is what you got when you added another 7 to 19.
Yeah.
Thank you. Okay.
Question B is about applying the Chinese remainder theorem. This is quite straightforward as well. So the Chinese remainder theorem to find the simultaneous solutions to x being congruent to 1 mod 3, 2 mod 5, and 7 mod 11.
So what are the integers x which simultaneously are in these 3 different congruence classes?
Again, the specification of the Chinese remainder theorem will be on the handout. And the first thing you need to do is just check that it's valid to apply it here. So
the condition for applying the Chinese remainder theorem, you can always apply it to sets of congruences like this, as long as the moduli are pairwise co-prime. That was the condition.
So the moduli 3, 5, and 11 are indeed pairwise co-prime. Easiest way to justify that is because they are distinct primes. Distinct primes can only possibly share the positive factor 1. So the greatest common divisor is always going to be 1. So the CRT Chinese remainder theorem does apply here. And describes the solution as x congruent to vi capital Mi prime, sum of these three modulo this thing here. This sum is going to go I equals 1 to 3, so it's 3 congruences. So the formula describes the solution as this.
So what are these things? Well,
The bi's are just the constants from the
3 equations.
capital M is the product of the 3 moduli, which is 15 by 11, which is 165.
Yeah.
The mi are, so the capital M1 is the product of the other moduli. So this is 5 by 11, which is 55. Capital M2 is the product of the other moduli, all except the second one, so 3 times 11, 33. Capital M3 is the product of the first and second, which is 50. So in other words, capital Mi is equal to Mi divided by little mi. But the little mi's are the
Different moduli. Little m1, little m2, little m3. Then the capital Mi prime are the inverses of these things modulo the appropriate little mi. So capital M1 prime is equal to capital 1
inverse modulo little m1, i.e. the inverse of 55 modulo 3. Now, there's not too many possibilities. Modulo 3 is either going to be 1 or 2. To work out what 55 is modulo 3, divide that by 3, goes in 1 squared of 2. 25 plus 8 remainder 1. So we're talking about 1 inverse, the inverse of 1 modulo 3, which is of course just 1. So capital M1 prime is the extra 1. Do the same for M2 prime. So this is going to be the inverse of 33 modulo 5. That's the same as the inverse of 3 modulo 5, which is 2. 2 times 3 is 6, which is coming to 1. Then lastly, M3 prime is the inverse of 15 modulo 11. It's the inverse of 4 modulo 11. 15 is coming to 4. Inverse of 4, so you're looking for that other integer that when you multiply it by 4 gives you 1 modulo 11. It's going to be 3 times 4 is 12, which is 31. So you've got all the ingredients there for that formula. So x is congruent to b1, which is 1, m1, which is 55, times m1 prime, which is 1. Now you must be careful when you're, there's potential to go wrong. These capital M1, capital M2, capital M3, you don't do any reduction of these. Because the role that they play here, and I'll remind you of it,
the role that these integers play is down to their prime factorizations. It's important that we keep this as 55 and we don't reduce it modulo anything, because the point about 55 is it's 5 times 11. And the point about 33 is it's 3 times 11. The point about 15 is it's 3 times 5. And that's going to be crucial when you know, for justifying this formula involving x.
The other things, the moduli are probably already reduced when you look at the original problems. But these inverses, yeah, we can reduce the, you know, we just choose the standard representatives of the congruence classes for the inverses. So it's P2, which is 2 times M2, 33 times M2 prime, which is 2. And then it's P3 times M3, which is 15, times M3 prime, which is 3. And the reason this is a solution, a simultaneous solution, is when you check what the status of x is modulo any of those moduli. So for instance, if you check what x is modulo 3, but by construction, this second and third term here have got a 3 in them, because they've got capital M2 and capital M3 in them. And they automatically have little m1, which is 3. So modulo 3, when you check x, this is just 0 and 0. These two things were designed to be inverses of each other, modulo 3. So they go away as well, just a factor of 1. So you're just left with 1, which was the B1. So this automatically satisfies the first congruence. When you check it modulo 5, by design, this first term and third term have a 5 in them. The 5 is in the 15, the 5 is in the 55. So those are congruent to 0 modulo 5. And the 2 and the 33 were chosen to be congruent, to be inverses of one another, modulo 5. So that gives factor 1. So you just left the 2, which is desired congruence class. Okay? So that's just a reminder of how this formula works. And so this is an expression for x for a representative of the congruence class modulo 125 of these solutions. So you just be maybe just checking if you can reduce this any. So it's 55 plus 66 by 2, which is 132, is it? By 45. So yeah, that probably can be reduced a little bit. Yeah.
Is it 165 or 125?
Yeah, probably. 165?
Yeah.
Yeah, 125 is yeah, it's right. Yeah, 165. Okay. Any
So you finish that off by just quoting the nice smallest remainder for that congruence class, which is whatever it is.
502.
Sorry?
502.
502. So that's not the smallest one. Right, so that's what that is. Modulo 165. So 165 probably goes in 3 times 300, 195, 495, 7. 7 modulo 165. Okay. Right then. Should we go on to the next one? 4 parts C. So 4 part C, the question was, faced with a general quadratic congruence, modulo an odd prime, and where this A is non-zero modulo P, so that means it is a genuine quadratic congruence. This integer A is not a multiple of P, because if it were, then this is effectively 0 modulo P. So if you got a genuine quadratic congruence modulo P, where P is an odd prime, show that this congruence has solutions if and only if the discriminant of the polynomial is a quadratic residue modulo P. There's just 4 marks going for this, so it's not too long a derivation. So you begin with ax squared plus bx plus c, congruent to 0 modulo P. And the beginning step in this is, in order to derive the solution for x, you want to stop there being both an x squared and an x there. So you want to express this in a different way, in the way where it's a square of a linear factor plus a correction. In other words, completing the square, it's often called. So in order to do that, we need to first arrange that this leading term, this order 2 term, is recognizable as a square of a quantity, modulo p. And we can do that by multiplying both sides by 4a. So when you multiply by 4a, you've got 4a squared x squared plus 4abx plus 4ac, and that's coming to 0 modulo p. Now the justification for this, and what exactly you're justifying, is the case that this is an equivalence. This is an equivalence since 4a, the number you've multiplied across by, is invertible modulo p. And that's true since p does not divide a. Okay, you're given that in the question, and p an odd prime. So the GCD of 4 and p is 1. Because 4 only has factors of 2 in it, 2 and 4. So the fact that p does not divide a, so a is co-prime to p, 4 is co-prime to p, so a and 4 have inverses, so the product 4a will have an inverse. And the fact that you've multiplied both sides by an invertible element means that this is a logical equivalence. You're free to multiply both sides by any element, and it will always give you an implication that if the top one is true, then the bottom one is true, where you've multiplied both sides by anything. But the only way you can go back, so if this second equation is true, then that also implies the first equation is true. In order to do that, you have to be able to re-obtain this one. In effect, divide by the common factor, and in the case of modular arithmetic, we mean multiply both sides by the inverse of 4a. But in order to do that, you have to be sure that it exists. Okay. So the second one is logically equivalent to the first, and now you can see that this is obviously a square. It's the square of 2ax. So we can use that to just rewrite symbolically the polynomial here. So this is going to be the square of 2ax plus something, and probably plus a correction. It's coming to 0 modulo p. So what goes here has to be the correct thing to generate 4abx. When you square this, it will generate 4a squared x squared, all right. So you want to put something here so that it'll generate the x term. You've already got 2ax, so you just need a b there. So that when you square this bracket, you get 2 times 2ax times b, which would be 4 times ax times b, so 4abx. So this thing here is just a b. And then you need to correct for the constant in the thing. You've got 4ac, but squaring this bracket is going to give you b squared. So you want to get rid of the b squared straight away, so you do minus b squared, and then we need the 4ac, go plus 4ac. That's where the discriminant, that's how the discriminant arises, that b squared minus 4ac combination. It'll be minus 4ac once we put it over the other side. But at the moment, it's just plus 4ac, because that's what it is up here. Yeah. So all I'm doing is just symbolically rewriting the polynomial on the left-hand side. But I've done it in such a way that there's no longer an x squared and an x appearing separately. I've just got a single x. Okay, it's squared. But now I'll be able to start to make x the subject of this equation. So this is equivalent to this bracket squared being congruent to b squared. See, the minus b squared becomes b squared minus 4ac modulo. No justification needed there. We're just moving something to the other side and changing its sign. But the next step is crucial to explain what's going on. Okay, intuitively, naively, we just want to take the square root of both sides. And effectively, that is what we're doing. But when we're speaking about modular arithmetic, we just use the language of quadratic residues, because we're not actually taking the square root of the integer in the real numerical sense. We're doing it in the modular arithmetic sense. So this equation will be equivalent to 2ax plus b being congruent to u modulo p, where and if, well, where providing such a u exists, or such u exist, put that in brackets, might be able to do this. So where u squared is u b squared minus 4ac. So u is a square root, effectively, of b squared minus 4ac. So you can make this last step if such congruence classes u exist. They don't always exist. They only exist half the time in modulo p. Okay? Because only half of the congruence classes modulo p are quadratic residues. So only half of them have these square roots. So i.e., providing b squared minus 4ac is a quadratic residue. If it isn't, what's the conclusion? If it's not, then no solutions exist. Because if b squared minus 4ac is not a quadratic residue, then it's impossible to square a bracket and obtain b squared minus 4ac modulo p if it's not a quadratic residue. Because there is no value you can put in the bracket such that when you square it, you get b squared minus 4ac. If it is a quadratic residue, then there is a u which you can pop into this equation here, and you can get rid of the square on that bracket. So then the thing will be equivalent to, providing the u exists, you can then make x the subject of this equation. X will be minus b plus u, and all of that multiplied by the inverse of 2a modulo. Okay, so it's just completing the manipulation to make x the subject of the thing. And this is the quadratic formula for congruences. It's the same, it's a similar thing that you recognize for equations. Minus b plus this u, which is the square root of b squared minus 4ac, divided by 2a. Except in modular arithmetic, we prefer to phrase it like this. Minus b plus a square root of b squared minus 4ac multiplied by the multiplicative inverse of 2a. And again, the inverse of 2a, this exists for the reasons above. These reasons we explained for the existence of the inverse of 4a, they're the same things that say that the inverse of 2a exists. I think we've addressed that equation. We've shown that the congruence has solutions if and only if the thing is a quadratic residue. If you can find these u's, you can put them into that expression, they'll give you a solution x. If those u's do not exist, then, yeah, just to make it clear, yeah, if it's not, so if b squared minus 4ac is not a quadratic residue, no solutions exist as the congruence star is clearly false. Or star is this congruence. B squared minus 4ac is not a quadratic residue. This is patently false because you can't square something to get something which is not a quadratic residue. So if this congruence is false, it's equivalent to the first one. So the first one is always false, so there's no solutions.
No quadratic formula. It's minus plus minus square root.
Yeah.
How come it's not plus or minus?
Well, yeah, it could be. So I didn't say here that there was one and only one u. I said providing such u exists. So if there's any u here, if you get one square root of b squared minus 4ac, then the other one, well, providing it's, you see, u could be 0. The discriminant b squared minus 4ac might be 0, in which case there's only going to be one solution. You'll have a multiplicity too. Yeah, but there'll only be one solution. So it's still the same thing. If U is a non-zero modulo P, you'll get one solution X. To get the other one, you can put in minus U. So there, yeah, so you can put in a comment, there will be two such U. Unless U is equal to 0, in which case there's only going to be U's common to 0 mod P, in which case there's only going to be 1. Okay, sorry for going over a bit. We've got to leave it there. So I'll be seeing you in the tutorials on Fridays. We can deal with any remaining issues then.
Oh,